Welcome back to this module review of caches. In this lesson I will show how, given a certain sequence of memory accesses and the direct map cache organization, we can determine if each access yields a hit or a miss. Let's now consider a small example. A processor generates the following byte addresses: 88, 104, again 88, again 104, 64, 12, 64, 72. Furthermore, it has a very small direct map cache with only 4 blocks, each of 4 bytes. Now we want to know for each access, will it be a cache hit or a cache miss, given everything we know until now. The first step is to compute the block address. From the previous slide, we know that the block address is given by the byte address divided by the bytes per block or the block size, and we can easily compute it. Then the second step is to compute the cache indices. And we know from the previous slide that the cache index is given by the block address modulo the number of cache blocks. All this information was given to us. Finally, we need to compute the tag, and the tag is given by the block address integer divided by the number of cache blocks. If we then do this for all the byte addresses that were given to us, these will be the result: 22, 26, 22, 26, mapping to cache index 22220, etc. And the tag will be 56564, etc. You can check that for yourself using your own calculator. Now we want to know for each access to a byte address, will it yield a hit or a miss? At the bottom here I show the cache before the access takes place. In the middle I show in red the cache access, the memory access that I will be focusing on, and at the bottom I will show the contents of the cache after the memory access has taken place. Right? Initially our cache is empty, as we can see, all valid bits are cleared. And then we access byte address 88 corresponding to block address 22. This maps onto cache index 2 and the tag is 5. And because our cache is initially empty, it will be a miss. And at cache index 2, as shown here, with tag 5, we will store memory block 22. Not only the byte 88, but all the bytes in that word in that memory block. This was our cache before. Now we access byte address 104. This corresponds to block address 26. Again, that maps to the same cache index 2, but it's not the one stored there because it has a different tag. So again, we will have a miss, and memory block 28 will replace memory block 22 in cache because they both map to the same cache block, to the same set. Again, I access 88. Again, it will be a miss because memory block 26 replaced memory block 22. So again, we will have a miss. Now I access block 104. This also maps to the same cache index, 104 again, but it has been replaced by memory block 22. So again, we will have a miss. Now we access byte address 64, corresponds to block address 16, which corresponds to cache index 0, which is another cache index than the 2 we had before. The tag is 4. It will be a miss because it's the first time we access block 16. But now we have the memory block 18 at cache block 0, cache index 0. Now we access 12. 12 maps onto corresponds to block address 3, and this maps to cache block number 3, as indicated here with the cache contents after the access. And finally, or for the first time we have a hit, we access byte address 64 again, which corresponds to block address 16. We look it up in the cache. We see that the tag of the requested block matches the tag stored in cache at that position, so we have a hit. And finally, we access 72. Oops, wrong way. We access 72, And again, we have a miss because it's the first time we access memory block 18. This concludes this lesson. Thanks for watching. In the next lesson, I will describe different metrics for evaluating the performance of a cache and how the cache hit time can be improved. Stay tuned.